All right, back to finish up our examples on electric potential. Number 2, the Van de Graaff generator can build up a potential difference of about 200,000 volts. Van de Graaff generator is the thing that you've seen probably in like a video or on TV at some point where you touch it and your hair stands up and it generates a lot of static electricity. We have one here. We will, if we haven't yet, we will use it. It is pretty fun to play around with. Anyways, it can build up a potential difference of about 200,000 volts near its surface. When you move near it, all of that built up energy that's in the charges near it is transferred to you in the form of 8 times 10 to the negative 6 coulombs of charge jumping between the generator and you. Once you get close enough, some of that charge will actually transfer to you. How much energy is actually transferred? Well, we can solve this using our new equation. The potential difference is equal to the work done, or the energy transferred, divided by the amount of charge. Now, the voltage difference, the electric potential difference that we're talking about, is the difference between the surface of the generator and you. Since the generator is collecting so much charge on it, it has a pretty large electric field around it, but that electric field falls off, and you, standing a little ways away, you are not as affected by that electric field. Okay? So what we're talking about with this voltage difference, the 200,000 volt difference, is between you, or what's the word I'm looking for? The Van de Graaff generator and you. We're going to move 8 times 10 to the 6th negative 6 coulombs of charge from the generator to you, or maybe vice versa. I think it's the other way around, actually. I think the charge goes from you to the generator. In any case, we want to know how much energy this transfers. We can find this by simply plugging our numbers in. We can rearrange this equation if we multiply both sides by Q so that we solve for the work that's done, the energy that's transferred. Q times V. The charge is 8 times 10 to the negative 6 coulombs times 200,000 volts. Notice we have a pretty small number. 8 times 10 to the negative 6 is like 8 microcoulombs, and a big number, 200,000 volts, or at least seemingly big. Calculating this tells us the work done, the energy transferred, is 1.6 joules. Okay? That's kind of interesting. How much energy is actually transferred, or how much work is done, those are equivalent statements, 1.6 joules. That's not a lot of energy. That's a tiny amount of energy, as a matter of fact. This is really low energy, and the reason is it's not because of the voltage. Okay, the voltage is pretty high. It's low energy because there's not that much charge passing through. Okay, 8 times 10 to the negative 6 coulombs is not a lot of charge. Remember, 200,000 volts means 200,000 joules per coulomb, meaning 1 coulomb of charge would carry 200,000 joules. But we don't even have anywhere close to a coulomb of charge. We have 8 times 10 to the 6th, negative 6 coulombs of charge. That's a tiny amount of charge. So it's low energy because not much charge is actually transferred. And this will feed into our next video. When we're talking about the transfer or motion of charges, movement of charges, we're really saying here that there's a low current. Okay? There's very low current. There's a low flow of charges. So this is actually, I mean, it'll shock you. It'll like zap you a little bit, but it's not particularly dangerous. Okay? It still could be dangerous under certain circumstances, but it's not particularly dangerous. The danger comes in when more charges are transferred. Or another way of saying that is when there is a bigger current. It turns out that the bigger current is more important than a big potential difference. Okay. Our next example will lead us to a unit that we use in the electrostatics unit, in the electricity unit sometimes, but we're also going to see it has a big use when we talk about our modern physics unit. What happens if one electron is moved through a potential difference of 1 volt? How much work is done? How much energy will be transferred? Well, we can solve that pretty easily. V equals W over Q. Again, we're going to try and solve this for W. We want to know how much work is done. One electron, that has a charge of 1 times 10 to the 6, or 1.6 times 10 to the negative 19th coulombs through a potential difference of 1 volt. Well, this means that the work done is 1.6 times 10 to the negative 19th joules. That's a tiny amount of work. That's a tiny amount of energy transfer. And you might say, well, that's so tiny. What if you are dealing with just single electrons or single protons moving through these voltage differences? Do you really want to have to tack on this scientific notation every time? Probably not. This amount of energy is so small that we have created an energy unit that is known as the electron volt. Electron volts are kind of fun. You just take the words electron and volt and you smush them together. Okay, that's a new unit, electron volt, to measure how much energy small particles receive or transfer from moving through a certain potential difference. So here's the definition. We kind of just defined it right there, but we'll write it again. The electron volt, like I said, you're just taking the two words and smushing them together. And as a matter of fact, the units for electron volt represent that as well. EV, E for elementary charge, V for volt. We just took the units and smacked them together. This is the energy transferred by one elementary charge moving through a potential difference of 1 volt. Okay? The amount of energy that is transferred. It could be gained, could be lost, moving for one elementary charge, either an electron or a proton, moving through a potential difference of 1 volt, either gaining, either a gain in potential difference or a loss in potential. Okay? The conversion between the two is 1 EV equals 1.6 times 10 to the negative 19th joules. So this amount of work that was done, 1.6 times 10 to the negative 19 joules, we could have just said it's 1 electron volt. Let me demonstrate this for you. If 3 protons are moved through a potential difference of 7 volts, how much energy is gained? Let's do it the old way first. We want to know how much energy is gained. We're going to go back to V equals W over Q. So W equals Q times V. Since it's 3 protons, I know one proton has a charge of 1.6 times 10 to the negative 19th. So I'm going to do W equals 3 times 1.6 times 10 to the negative 19th coulombs. Move through a potential difference of 7 volts. The work done, I'm going to have to squeeze this in, I apologize. The work done in that case is 3 times 1.6 times 10 to the negative 19th times 7, 3.36 times 10 to the negative 18th joules. 3.36 times 10 to the negative 18th joules. Now, again, that was kind of annoying because we had to use a scientific notation. We have very, very small amounts of charge. We could also have done this. V equals W over Q. Rewrite it. W equals Q times V. With this equation, and I only want you to do this with this equation, you can actually use the charge in elementary charges. 3 protons is simply 3 elementary charges. So 3e times 7v, guess what? 3 times 7 is 21. That's 21 electron volts is the amount of work that gets done. And just to prove that this is the same thing, 21 EV, if we convert that, since 1 EV is 1.6 times 10 to the negative 19th joules. If I take 21 and multiply by 1.6 times 10 to the negative 19th, look what I get. 3.36 times 10 to the negative 18th joules. So we see that these are equivalent to each other. Now, a lot of times, sometimes you have to use one, sometimes you have to use the other. I think this is almost easier to do, but you've got to recognize when you have to find the work done in joules. Our last example, a battery has a potential difference of 6 volts between its terminals. If a certain charge moves from the positive terminal to the negative terminal of the battery and loses 0.03 joules of electric potential energy along the way, what was the magnitude of the charge? The potential difference is caused by the electric field in the battery. If the charge moves from the positive terminal to the negative terminal and it loses this amount of energy, remember that 6 volts is the amount of energy that gets lost per amount of charge. If we know that and we know how much energy is lost, we can predict how much charge actually moved. V equals W over Q. This time we're solving for Q, so I'm going to multiply both sides by Q. I end up with work equals Q times V. I divide both sides by V. I end up with Q equals work over V. The work was 0.03 joules divided by the voltage difference of 6 volts. Q equals 0.005 coulombs of charge. Or, if you want to put that in scientific notation, 5 times 10 to the negative third coulombs. Electric potential is pretty straightforward as far as the material goes. Really, the concept is the most important part, okay? The math at this stage you should be able to do. The concept is the most important part. What does it really mean? It is the amount of energy transfer per unit of charge between 2 points in an electric field, okay? You've got to understand that. You've got to work to make sure that that makes sense to you. Like I said, this is the bridge between electrostatics and circuits. When we come back, we're going to be looking at what an electric circuit is and how they work in a very general sense. I'll talk to you later.